Chapter 21, Problem 15. Which of the following is an optically active aldehyde? So the first thing I'm going to do is focus on the word aldehyde. So an aldehyde has to have a carbon with a double bonded oxygen and a hydrogen. And then on the other side, it could either be a carbon or a hydrogen. So minimally double bonded O with a hydrogen. So the first one has an OH. There's no double bond whatsoever. This functional group is called an alcohol. That's not an aldehyde. The second one, we have that double bonded O at the very end, and there has to be a hydrogen there if that carbon is going to have 4 bonds. And same with C. But in D, that carbon that has a double bonded O has 4 bonds already. So there's a carbon on the right-hand side, there's a carbon on the left-hand side. So there's no hydrogen attached to that carbon. That's called a ketone. So we'll get rid of that. So these two are aldehydes. Okay, now let's talk about being optically active. So optically active means it can bend or rotate polarized light. So if you were to take a light source and this will be polarized light that my arrow is illustrating here. And we're going to shoot it through a tube that contains our compound. So if it doesn't rotate it, you would expect the light to come out the exact same direction that it went in. But if it is an optically active compound, the light will come out at a different angle. So it is considered being rotated. Okay, now, in order to be optically active, you have to be chiral. So lots of new definitions in this problem. So chiral molecules. So the definition of chiral is asymmetrical. But what causes the asymmetry is you have a carbon bonded to 4 different groups. So for example, if you had a carbon with a hydrogen, a carbon, a 2-carbon chain, and a bromine. So these are 4 totally different groups. So I would say that this is a chiral carbon. And I would say that the molecule as a whole is chiral. And because it's chiral, it's automatically optically active. Okay, so we're looking for a carbon bonded to 4 different groups in our structures. Now these are skeletal structures, and so we're not going to see all the atoms. So it helps to draw them in. So I'm just going to do it for the aldehydes. So we've got a carbon here, a carbon here, a carbon here, carbon here, and a carbon here. And then carbon likes to have 4 bonds, so we're going to give it the number of hydrogens to total 4 bonds. So starting on the left, that carbon we could see has just 1 bond, so it needs 3 hydrogens. So because it has multiple hydrogens, it cannot be a chiral carbon because it has to have 4 different groups, and 3 hydrogens is 3 identical groups. Then the second carbon, we see a bond to the left, a bond to the right. So he needs 2 hydrogens. So again, if you have multiple hydrogens, you can't be a chiral carbon. And then the carbon that's sticking down, he needs 3 hydrogens, so he's not chiral. The carbon on the right, he has a double bond, so that's out right off the bat. So the one remaining carbon is the one second from the end, and we see a bond to the left, a bond below, a bond to the right. So he's going to need 1 hydrogen. So he has surrounding him the carbon below, the carbon to the right, but the carbon to the below and the carbon to the right are totally different because one's a CH3 and one has the oxygen. And then it has the group to the left, which is a 2 carbon chain, and it has the hydrogen. So those 4 groups are totally different. So that's an optically active aldehyde. The next one we have to put in our carbons. Now, the ones that are on the ends, those have 3 hydrogens. So those are definitely not chiral. The one that's second from the end has 3 identical CH3 groups. So that's not chiral. And then the chiral that is second from the end has 2 hydrogens. So he's not chiral either. So there's only one answer, and that's B.